Hey Chem, Mr. Pajek here. I know some of you have been working on the material that Mrs. D has posted on the OneNote, so to kind of try and help make some of that content a little bit more digestible, I figured I'd make a summary of sorts. So this video mostly addresses the content that's introduced in the collision theory gizmo. Chemical reactions are kind of like demolition derbies. In demolition derbies, cars and trucks drive around in the demolition ring colliding with each other. The goal here is to be the last operational vehicle. If we think about the kinds of factors that cause collisions to disable other vehicles in demolition derbies, we might think of things like speed, meaning the faster you go, the more damage you're causing, and therefore the more likely you are to break down someone else's car, or orientation, where collisions with like T-boning the vehicle or colliding with the engine of another vehicle, that's more likely to make that vehicle stop working than if we were to like crash into its trunk, for example. So in chemical interactions, molecules are like vehicles. So these little balls that are kind of moving around, bouncing around on the screen, we can kind of think of these as being like cars in a demolition derby. So the molecules bounce around in their reaction vessel, whether that's the atmosphere or a flask or a beaker or whatever it happens to be. They're moving around and bumping into or colliding with other molecules, just like the cars in demolition derbies moving around and colliding with other cars. In the case of demolition derbies, though, the collisions result in making cars stop working, while in chemical reactions, collisions are a mechanism that decides whether or not reactions will occur. And we refer to this as collision theory. So the collision theory gizmo simulates the impact that different variables have on molecular collisions and therefore reaction rate, whether or not collisions will or whether or not reactions will occur. I want to summarize and kind of rephrase what some of these factors are and why they impact reaction rate. So in this video, we're going to look at 5 of those factors. So we're used to seeing chemical reactions expressed in equation form. In this case, carbon dioxide and nitric oxide are reacting to form carbon monoxide and nitrogen dioxide. But we could also represent this kind of equation in particulate form, where different colored balls represent different kinds of atoms. The black one is carbon, the red one's oxygen, the green one's nitrogen. And so here's our reactants on the left and our products on the right. So collision theory suggests that in order for reactions to occur, our reactant molecules need to collide. Nitric oxide, needs to collide with carbon dioxide and vice versa. They need to be able to bang into each other. Now, let's consider 2 possible orientations that nitric oxide might take. So these 2 different nitric oxide molecules are chemically identical. They both contain a nitrogen, they both contain an oxygen, exactly the same chemically. The only difference here is how they're positioned in space. So let's think about the possible collisions that could occur between this nitric oxide and carbon dioxide and this nitric oxide and carbon dioxide. In the case of the first, let's imagine that this top nitric oxide comes whipping at carbon dioxide in this orientation, meaning nitrogen is coming into oxygen. Well, what could happen in that case then is that the bond between carbon and oxygen could break, and a bond between nitrogen and oxygen could form. And notice now that our reactants are the same as our products. So in this case, orientation allows for the reaction to proceed. Let's consider, instead, the bottom nitric oxide. Imagine that this guy is whipping in towards carbon dioxide in the same way as we saw with the top one. But instead of nitrogen coming in first, we've got oxygen coming in first. Well, that means oxygen and oxygen are getting together. So our products might look something like this. Turns out this doesn't happen. Instead, there's just no reaction. But really the point is that if we observe our reactants now, notice that they don't match our products. So based on this, based on how the molecules were oriented in 3D space, decided whether or not a reaction could proceed. In the case of the top one, a reaction could proceed because it was oriented in the correct position. In the case of the bottom one, a reaction would not proceed, again, strictly because of orientation. So that's the first factor that this gizmo is kind of looking at, is orientation. Orientation is important to deciding whether a reaction can occur. Another variable that the gizmo investigates is the impact of temperature on collisions. And if we kind of think about what's going on here, I think it's pretty sensible. So in the left here, we see this low temperature system. And we know from studying kinetic molecular theory in grade 11 chemistry that low temperature means low kinetic energy, means that things are pretty sluggish. They're moving around pretty slow. Whereas in the system on the right, this high temperature system, well, that means that there's high kinetic energy, and so the molecules are whipping around with quite a lot more speed, right? They're zooming around, they're banging around a lot more. So think about what that means for collisions then. If things are moving slowly, there will be less frequent collisions. They're not going to bang into other molecules as often because they're just not moving around as fast. Whereas in a high temperature environment, well then, since they're moving around faster, they're going to be colliding with things more often. Think also about the energy of collisions. In the low temperature environment, when collisions happen, it's kind of like if you're shuffling your feet, not moving very fast, and then you bump into someone, well, it's probably just a light little bump. Whereas if you're sprinting and then you bang into somebody, well, you might knock them down. There's a lot more force, there's a lot more energy in that collision. So high temperature systems mean that there's more collisions and higher energy collisions. Another way that we can kind of think about this is with an analogy where let's imagine that we're in the classroom and I'm blindfolded and I'm wandering around the classroom. And I wander around at two different speeds. In the first case, I'm walking around the classroom blindfolded. Well, if I'm walking around the classroom, I'm not going to be banging into things too much, but occasionally I'll bump into things. I'll collide with things from time to time. And when I bump into things, again, probably not too hard. Conversely, if I'm sprinting around the classroom, well, now I'm going to be bumping into things way more often, bouncing off the walls, bouncing off people, bouncing off furniture, way more collisions happening, right? And when I bump into people, there's more energy in those collisions. So we've so far seen two different factors that can impact collision theory, right? We said that the orientation of molecules is important and temperature is important. The third one here, we can kind of help visualize. So these are two side-by-side screens that we were taken out of the Gizmo tool. In the one on the left, we can see very few reactants. There are some reactants there. It's a low concentration. In the system on the right, we can see quite a lot more reactants. So this is our left system, this is our right system, quite a lot more reactants. It's a much higher concentration because they're occupying the same volume here. And we know that concentration is moles per unit volume. So the system on the right has way more reactants, means that it has a higher concentration. Well, again, let's think about this kind of blindfold analogy. Let's build on that a little bit. Let's imagine that we're in the classroom. And in one case, there's 5 of us in the classroom. And all 5 people are blindfolded, and we're all walking around the room. From time to time, those blindfolded people will bump into each other. Let's consider everyone is in the classroom. We've got like 30 people in the classroom, and they're all blindfolded. Same size classroom. We're all wandering around blindfolded. We're going to be bumping into each other quite a lot more often because there's just less available free space that wouldn't be us banging into each other. So by increasing concentration, we increase reactivity or reaction rate because there's just more collisions happening because there's less free space. So factor number 3 then is concentration. The Gizmo also explores surface area. So I want to kind of flesh that out a little bit, but I want to think about it in terms of not a chemical reaction, but the process of solvation, meaning stuff dissolving in water. So we all know, whether through experience or just through intuition, that if we took a cube of sugar, imagine we've got a cube of sugar, and we put it into a beaker of water. And in another beaker of water, same exact size, same volume of water, same temperature of water, we take another equally sized sugar cube, so same number of moles of sugar, and we throw it into a mortar and pestle, and we grind it up into grains of sugar. And now we take those grains of sugar and we put them into that second beaker that has the exact same conditions as the first. We know that the grained sugar, the one that we ground up in the mortar and pestle, that it's going to dissolve more quickly than the cubed sugar. And we know this is the case from the solutions unit last year when we thought about the solvation process, right? We know that in solvation, stuff has to break apart so that water can surround those individual grains of sugar. So we've got solvation occurring here. Well, let's kind of think about what's happening then. When we have a low surface area, meaning that cubed sugar, a lot of the molecules of that sugar are kind of hiding away in the center of the cube. Water can't access them. And since water can't access them, water can't surround them, right? They've got to be able to break it apart. So to get at those middle kind of grains, to do that, water first has to pick away at these outer grains, which will then expose the inner grains. In the Gizmo, they explore reactivity, which has kind of the same principles at play here. Where in the system here on the right, we can see a low surface area environment. This is like that cube of sugar. Well, for a reaction to occur, we know that this molecule has to be able to collide with these reactant molecules. So right now, the only possible collisions are the ones that are on the exterior of our cube. The ones that are hidden away in the middle, they can't react because they can't be exposed to this other reactant, right? Whereas in the system on the left here, where we have very high surface area, this is like our granulated sugar, the one that's been ground up. Well, now we've got reactants, basically all of these cubed sugars, as it were, they're exposed to all of these other reactants. So collisions can happen to more molecules than was in the case here, where we had low surface area, right? So by increasing surface area, we're increasing the amount of reactants that are exposed to other reactants, and therefore we're increasing the number of reactants that are possibly able to collide, and therefore we're increasing the number of reactants that could cause reactions or undergo reactions. So again, in this case then, surface area is our fourth variable, and its increasing surface area increases reaction rate. All right, so 4 down, 1 to go. This last one, to be able to understand it, let's think back to that very first day of class, that last little bit after the quiz we did on the first day. We went into the lab, and the experiment that most people gravitated towards was this one where we put yeast in hydrogen peroxide. And we know that hydrogen peroxide, we use that for things like treating cuts to make sure we don't get infections, right? So hydrogen peroxide will normally, if left on the shelf, it will break down following this chemical equation. It will break down from hydrogen peroxide into water and oxygen. That'll happen no matter what. Even if you open the bottle, you throw it back into the shelf or into your medicine cabinet or whatever, it's sitting in there, you leave it for long enough, eventually, when you use this on a cut, it won't burn anymore. And the reason for that is because we don't have much hydrogen peroxide left in the bottle anymore. Most of it has been changed into water and oxygen, and water and oxygen on a cut don't burn. So let's think about that reaction that we did in class in the lab. When we added yeast to hydrogen peroxide, we saw bubbling occur. That's what these images are. This is something called elephant's toothpaste, which is hydrogen peroxide plus dish soap. And then you can see this hand is about to add in the yeast, and it'll cause it to bubble up. And the bubbling is evidence that we're producing oxygen. It's speeding up the rate of this decomposition. We say that yeast is catalyzing the reaction. It catalyzes or speeds up the breakdown of hydrogen peroxide into water and oxygen. A catalyst is something that speeds up a rate of reaction without itself being changed or consumed in that process. So that's our fifth factor here, is catalysts. And the gizmo explores catalysts as well. So in the gizmo, our catalyst is this little purple thing. I'm just going to pause this for a second here. It's this little purple thing, and it's kind of got these little grooved indentations on the inside. So these little grooves, these little pockets, are called ligand-specific sites, meaning that some of these sites will only bind to this reactant, some of these sites will only bind to this reactant. They specifically bind specific things. So let's play this animation and notice what the catalyst is doing, and think about kind of what you saw when you were doing the gizmo. But it bumps in, picked up a reactant, and immediately bumped into another one. Picks up a reactant, it's kind of bumping around. Oh, it bumped into the blue one. When that happened, notice it let go of the reactants because they had turned into products. Now it's had these blue ones for a while. It's just bumping around, waiting. And eventually, it would bump into our green and orange reactants, and that would trigger our reaction to occur, right? So let's kind of think about what's happening with the catalyst, what it's doing. Well, one, it's binding to specific reactants. So it's holding those reactants in kind of a favorable orientation for reactions to occur. And then two is when it picks up that second reactant, well, now it's holding those two different reactants, the blue balls and the green and orange ball, it's holding them in close proximity to each other so that they're ready to interact. They're ready to react right away. So it's holding them in specific orientation, and it's holding reactants in close proximity. Notice again, the purple thing, it doesn't change, it isn't altered in any way. It's really just this vehicle for changing the rate of reaction, for speeding it up. So to kind of summarize all this information that we've talked about to this point, there are a few different points we'd want to make. The first is that reactions are the result of molecules colliding with each other, and we call this process collision theory. So again, kind of like a demolition derby. We said that collisions and therefore reaction rates are impacted by 5 factors, and those 5 factors are orientation, meaning that molecules must collide with, quote, correct positioning. They have to be oriented in the right way. Temperature, where increasing temperature increases the kinetic energy of molecules, means that they're moving around faster and with more energy, meaning that there are more frequent and higher energy collisions. The third factor was concentration, where higher concentrations lead to higher collision frequency because there are just more reactants around to collide with. The fourth was surface area. Think about those sugars, so the cube versus the granulated sugar, where higher surface area means that there's more reactants that are exposed, fewer that are kind of hiding around in this inaccessible location, meaning that there are more reactants that are available to collide and therefore faster reaction rates. And then the final factor was catalysts, where catalysts again increase the rate of reaction without themselves being changed or consumed in that process. And they do this by holding reactants in orientation that are favorable for reactions and by placing reactants in close proximity with each other.